So I selected here in this lecture, I think there are 13 exercises. Of course, we won't have time to do all of them. So we're going to do a few today, maybe 4 or 5. And then I'll post the solution to the other ones or just the final answer. You can use them to practice for the upcoming final exam. So let's get it started then. Let's do these ones from the last lecture first. So all these, as I mentioned, sorry, let me just change the screen here for folks that are at home. All these ones, you recognize this from one of the last lectures. This came from midterms and final exams. So here we have one. The question is very simple. We are given a transfer function. And the question is, which of the following time domain signals best describes the response of the function h of s given below to a unit step input? A, B, C, or D. So I'll give you some time to look at this and see how you would approach this question before we solve it together. What would be the first thing you would be looking for here? How would you approach this question? Any ideas? What would you look for first? Yep. Poles and zeros. Yeah, determine what kind of problem we have, underdamped, overdamped, and so on. Yeah, we could look at that. We can also look at these 4 graphs and see the difference between them. What differs between these 4 graphs? Well, they have the same final value, and that doesn't change. They all go to 1, which is indeed what would happen with this transfer function if you give it a step input. So that is the same for all of them. What else do they have in common? They are all overdamped, underdamped, critically damped. What kind of system time response are we looking at? All of them are? Come on, folks. I know it's early, but it doesn't hurt to answer a few questions. What kind of system are we looking at? Underdamped, overdamped, critically damped, unstable, marginally stable, or undamped? Underdamped. Very good. All of them are underdamped. And how can we tell? We can tell because we see these oscillations. We see an exponential, and we see a sinusoidal waveform as well. We see some oscillations even here. It's not a perfect sinusoidal wave, exponential waveform. We see that it has a little bit of overshoot in there. What is the difference between them? As we move this way, what is happening to the damping ratio between these 4 graphs? Is it increasing or decreasing? What is happening to the damping ratio? Without calculating anything, what can we tell? Is the damping ratio increasing or decreasing? I have time. I found a comfortable seat here. I can wait. Yeah. Right. So very good. So the damping ratio dictates how much energy dissipation there is in the system. And the smaller the damping ratio, the more oscillations we will see before the system settles. So as you see here, we are damping the output more and more. So the damping ratio is increasing as we go from A to D. That doesn't really answer our question. It's just an observation we can make. They have, all these 4 functions have different damping ratios, but you can really tell which one is which here based only on the damping ratio. Sorry, my slide here is stuck. Okay. What else can we, so we see that the damping ratio is increasing. What else can we tell here? What is now the difference between them? What else can we say? What is another characteristic other than the damping ratio being different? We can see across these 4 functions. right? Right. So you're trying to say is the settling time between the four functions is different. Very good. The settling time is different. So that's how we're going to determine, look at this determine which of these graphs correspond to the transfer function. So let's do that then. If the settling time is really what is different between these four functions, let's find the settling time of equation h of s, and then see what we get from there. So to do that, we first need to normalize the transfer function and make sure that we have s multiplied by 1. So I'm doing here is dividing everything by 4. Don't forget that a critical step. And with this, we can write the transfer function in the standard form. And now find the damping ratio and the natural frequency. Why? Because the settling time for this function is 4 divided by omega n times zeta, or the real part of the pole. Another way to do this would be to find the poles of this transfer function. Look at the real part. The real part is zeta omega n. And remember that. Well, let's do it more traditionally. So what is the, we need omega n, we need zeta. So omega n we can find by now comparing the standard form of the function with the function we have. So we have omega n squared. Sorry, this is omega n squared equals to 0.25. So omega n is 0.5 radians per second. And we can do the same for the damping ratio. 2 zeta omega n equals to 0.25. Now we are looking at that. And with this, we can find damping ratio as 0.25 divided by 2 times 0.5, which is 0.25. So now that we have the damping ratio and omega n, we can find the settling time. Settling time is 4 divided by zeta, 0.25 times omega n, 0.5, and this is approximately 32 seconds. What does it say? Does it mean? It means that it will take the system 32 seconds for the output to be within 2% of its final value. It will take the system 32 seconds for the output to be between 1.02 and 0.98, because that's 2% of the final value, which is 1. Right? And that's what you can see in figure B. All right, so that's the answer to this question is B. Did anybody get that? Yeah. Sorry, could you speak up? I can't hear you. No. If you, unless, so for those that are at home, the question was in the final exam, do we need to show all the calculations? No, you don't have to, but unless the question justify your answer, which is very likely to. Yeah. Okay. Any other questions about this one? Any questions from home? No. Move on. So, yeah. Did you have a question? Oh yeah, sure. Correct. No, it's only underdamped, regardless of the input. Yeah. Okay. We good? Yeah. All right, so let's do another one. There are no more questions here. Sorry, my PDF here is stuck. Let me just open it again. There we are. Let's do exercise number 2. So here we have a different concept. We have the poles of 3 functions are shown in the S-plane. Circle the correct statements, and you're given the time response of what these poles would create. We have 5 options here, and we want to find the correct statements or statement. So I'll let you think about this before we solve it together. How would you approach this question? Take a look at it and see if you can find the answer. I think the first step is to identify which pole gives each of these time responses, and then from there we see which one of those statements hold. So let me ask you this then. Which of these 3 curves corresponds to pole P0? W of t, why is that W of t? Because it's an exponential, right? It's an exponential waveform, and because P2 is real, is a real number, right? So we can say that because P2 is a real number, is a pole, it's a real number, the damping ratio is either 1 or greater than 1, and that only gives exponential waveform. So P0 corresponds to W of t. Does that make sense? Does that make sense? Yeah. Correct. Exactly. That's exactly what it is. P0 has no imaginary component, and therefore, if it has no imaginary component, it cannot have any exponential component. Any sinusoidal, excuse me, cannot have any sinusoidal component, can only have exponential components. And the only function that matches that criterion is omega Wt of t. Or omega, that's omega, W. Okay, now we are left with P1 and P2. So now which one is X, which one is Y? So to answer that, let's look at these poles. And before we even look at the transfer function, which one of these poles, P1 or P2, has the smallest damping ratio? Which one of them has the smallest damping ratio? Sorry? Well, Y of t has the smallest damping ratio. Yeah. And then for P1 and P2, which one has the smallest damping ratio? If you just look at the location of poles without looking at the curves, is P1's damping ratio greater or smaller than P2? Where is the damping ratio again? The damping ratio is this angle here, is proportional to that angle. Remember from the last lecture. So P2 has a smaller damping ratio than P1. P2 has a smaller damping ratio than P1. With this is enough to answer the question, but which one of these two has the greatest natural frequency? P1 or P2? Which one has the greatest natural frequency? Where is the natural frequency again? That's the distance from the pole to the origin. So you can say that P2 has a greater natural frequency. So P2 having a greater natural frequency, it will result in oscillations having faster frequency. Oscillations will happen with a faster frequency. That's one thing we can tell about P2. Another thing we can tell about P2 is that because it has a smaller damping ratio than P1, it would lead to higher oscillations as well in magnitude. So from the natural frequency, we can infer that a P2 will have a higher frequency of oscillations. And from the damping ratio of P2, that is smaller than that of P1, we can say that it will result in more oscillations overall. So P1 is therefore X of t, and P2 is Y of t. Because P2 has a smaller damping ratio, more oscillations. You can also tell that by the fact that at the frequency of oscillation of omega of t, you see more oscillations happening faster there, meaning that it requires a greater natural frequency. And that's indeed the distance of P2 to the origin. So if P0 is W, P1 is X, P2 is Y, which one of these statements is correct? We only have P0. No, P0 is, well, which ones are correct? P0 is Y of t. I think the only one that is correct is B. Yeah, so I think it's showing. I think that's the only one that is right? There's only one correct statement. All right, so if there is no questions now, I'll let you answer exercise 3. Based exactly on what we discussed. It's exactly the same type of question, but now we have a different set of poles and different time responses. So start by associating each time response with a set of poles. And then we'll take it from there. We'll see which one of these statements is correct. Okay, so let's start with P3, which is the easiest one. Which signal does P3 correspond to? Y of t? Why is that Y of t? It is Y of t, but why is that Y of t?
Y of t is like unstable.
It's unstable, right? Yeah, exactly. So Y of t is unstable, but we can say more formally that the problem here is that the real part of P3 is positive. And if the real part of P3 is positive, the exponential associated with it increases over time. And you can see that in the waveform of of Y of t. There is indeed an exponential here that is bounding the signal. And this exponential is indeed growing. Another thing we can say is that this signal Y of t has an imaginary part because it has a sinusoidal component to it, and that is exactly what we see in P3. If P3 was placed here, call that P4, what kind of signal would we see? Would we see an growing exponential waveform without any sinusoidal part, right? So P3 is indeed omega Y of t. So this is Y of t. What is P2? Exactly. So P2 is W of t because it's only an imaginary number, purely imaginary. We don't have a real component. And if you don't have a real component, there is no exponential associated with it. So the system oscillates indefinitely. So P2 is indeed omega of t. And then P1 must be the one that is left, which is X of t. And this makes sense. If you look at X of t, we have an underdamped system. And this underdamped system has both exponential and sinusoidal components. P1 has both imaginary and the real components, so they all match. Okay. So now based on these 5 statements, which ones are correct? We have C and E that are correct. Yeah, P3 are the poles of Y, P2 are the poles of W. And I think that's about it. So this one has 2 correct statements.
Just a question about explaining why the poles P1 and P1 prime are related to XT. In the same way that we explained why an unstable function Y of t is like an increasing exponential, is it also true that we could say because P1 and P1 prime are negative, the exponential?
that's a good point. So in P3, we have a positive real part. We see the exponential growing. P1 has a negative real part. We see its exponential decaying. And we can actually find it here. If you look at x of t, here is the exponential. Something like that. All right? That is bounding the sinusoidal waveform and is decreasing because its real part is negative. So consider the system shown. We have here a plant and we have a controller. This controller before, we just put a value of k here. But now we have a transfer function that serves as the controller. We don't need to worry about what that transfer function is doing exactly as the controller. We'll see that later. For now, that's just assuming that our controller takes this format. We have a plant that we are trying to control. We have a desired signal, a output signal, and we have control over the value of k and the value of a. Those are two constants. And as designers, we can choose what to put in k and what to put in a. But as we saw before, this, when you multiply everything, will be a second order system. We need to be careful with the choices we make here because we may make this system underdamped, unstable, and so on. So the question is, find the transfer function y over r and specify the controller gain and the value of a so that the response to a unit step input has an overshoot of no more than 25% and a settling time of no more than 0.1 seconds. So we have two variables and you're given two design constraints, settling time and percent overshoot. So with that, we should be able to solve for a and k. Well, let's start by finding the closed loop transfer function. Now, at this point, it should be very clear that the transfer function is y over s, that is 100k divided by s plus a times s plus 25, all divided by 1 plus the same thing. Okay, and then y over r is 100k divided by s plus a, s plus 25, divided by, find a common denominator there. At this point, you probably realize with practice that what you have to do is to add the numerator to the denominator when you do the closed loop transfer function as a shortcut. And what you have here, now we can cancel out the denominators, this one and that one, and then multiply out what you have at the bottom here. This is 100k divided by s squared plus 25 plus a s plus 25a plus 100k. Okay, so that's the closed loop transfer function. This must be, at this point, really clear. So the question tells us we want to determine A and K such that we have a percent overshoot of 25%, a damping ratio of 0.1. What do we do next? Exactly. So what you're suggesting is because we have a specific overshoot, we know exactly what damping ratio we need to achieve that percent overshoot. So we can tune A to give us that, right? And that will also be a function of omega n. So we need to identify omega n and zeta that it will meet those requirements first. So let's do that. Let's see what omega n we need and what zeta we need in order to meet the requirements. So let me write the transfer function here. Format omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. So we want a percent overshoot of 25%. With the percent overshoot, we can identify the damping ratio that will lead to 25%. And to do that, we can simply equate this to the equation for the percent overshoot, which is 100 exponential of negative pi zeta divided by 1 minus zeta squared. Now notice here that I use 25% as 25, not 0.25, because that 100 is already there to account for the percentage. And also always be reminded that this equation only holds for underdamped system, meaning that we cannot have a damping ratio outside of those bounds. This doesn't work. So what do we do now? We can divide 25 by 100. That is 0.25. We can take the natural log of both sides of this equation. And we have this as a result. That square root is kind of a bit inconvenient there. We can square both sides of the equation to get rid of it. So we have natural log of 0.25 squared. Then I can move this to this side, equals to pi squared zeta squared. And what else can I do here? Now I can solve for zeta squared by doing what is left here, the log of the 0.25. The squared equals to zeta squared times pi squared plus that, and then zeta is the square root of natural log of 0.25 squared divided by pi squared plus log of 0.25 squared. And this is, according to my calculations here, 0.4037. Okay, so here is one checkpoint. If we got a zeta smaller than 1, right? If we accidentally got a zeta greater than 1, then there's a mistake somewhere, because it can only be between 0 and 1. So you can check our result that way. Okay, so practice this. This is a simple, very simple math equation to solve. And yet there's a lot of mistakes happening during tests. And that could have been avoided with some practice, because it's always the same. You're giving percent overshoot, calculate the damping ratio from it. Any questions? So what have we answered here is to get a percent overshoot of 25%, we need the damping ratio to be 0.4037. The other requirement, are there any questions about the damping ratio part? No? The other requirement we have is that we want a settling time of 0.1%. And you know that the settling time is 4 divided by zeta omega n, or the real part of the pole, the magnitude of the real part of the pole. And with this, we can find our required omega n. So Ts is 0.1. And you have 4 divided by zeta, 0.437 omega n. With this, we can find omega n. And this is 99 radians per second. So to meet these requirements, we need those two values to hold. Right, yes, yeah. So now that we get omega n and zeta, we have to specify a and k. We can just equate the values of the standard form with the function we have. So let's do that next if there are no questions here. So we're gonna minimize these guys here, oops. Just minimize that part. Now that we have zeta and omega n, we can go back to our standard form and equate the two. So we have 2 zeta omega n equals to, sorry, this is for some reason not showing. 2 zeta omega n is equal to a plus 25. And we have omega n squared equal to 100K plus 25A. This is coming by equating the equation we have with the standard form. Now we can start with the first equation, 2 zeta omega n equals to A plus 25, because you have everything there. All we need is A, that's what we're going to solve for. So 2 times zeta, 0.4037 times omega n, 99, minus 25 equals to A. A is 54.9. Now we can go to the second equation, omega n squared, which is 99, minus 25 times A, 54.9, divided by 100 is equal to K. And this is coming from that equation. And with this, we find K equals to 84.28. Okay, so if you have A at that value, K at that value, we can meet the requirements we need. And this is a very interesting example where we have a plant to control. The plant we have no control over. It has that specific transfer function because that's how the system works when you can't change it. But you can change the behavior of the entire system by adding this controller to it and then tuning the controller in a way that you can find a good balance between overshoot and settling time. This is a good example of a more sophisticated control system that we can use. Any questions? Yep.
In the first line of the green equation, is there like a name for that equation specifically?
Which equation? Sorry.
2 zeta WN equals A plus 25.
Yeah.
Like, is that, where did that equation come from?
Right. Yeah. So we are equating the standard form, or did I put my pen here? We're equating the standard form with the equation we got. So we're looking at this 2. Right? And then we can take 2 zeta omega n as what multiplies S, and what multiplies S turns out to be A plus 25. And then what multiplies omega n is 100, what multiplies S to the power of 0 is omega n squared. Turns out to be 100K plus 25. Does that answer the question? Yeah, we're just equating the coefficients of S on both the equation we have and the standard form for it.
Yeah. So on the top of the equation, omega n is 100K, then omega n squared.
Right.
And then on the bottom, it's 100K plus 25A.
Right. Yeah. Okay. So good question. So we have omega n on top of the equation as being 100K, and the bottom of the equation, omega n is now 100K plus 25A. So that's indeed different, but it doesn't really matter because what is happening is if we add a number here plus B, what are we doing? We are scaling the transfer function. Transfer function that would have a response like that will now have a response that is like this, but it will follow exactly the same shape. The shape is only dictated by the denominator of the transfer function, by where the poles are. So if you add anything to the numerator that is just a constant, we're basically just scaling it up or down. But everything will shift accordingly. The damping ratio doesn't change. The percent overshoot doesn't change. The settling time doesn't change. The natural frequency doesn't change. Right? So that's okay. We can just look at the denominator of the transfer function. They are not the same, but the fact that they are not the same will not affect the shape of the time response. Let's put it this way. So the equation is, I ran out of space there, 100K divided by S plus something, I don't know, 5S plus 100K plus 25A. when you don't have this on top there. But what you could do is do 100K plus 25A here. Take this guy, move it over here, and then add this on top there. Right? And all I did here was to add this constant in front of it. I can cancel this 2 out. Right? And then I go back to the same thing I had before. So now I have omega n squared here. And also I have omega n squared here. They are the same. The only difference compared to where we started from is that we have this in front of it. It's just a scaling factor. The transfer function itself doesn't change shape, doesn't change the percent overshoot, doesn't change the damping ratio. That's all the same, but we just added that again in front of it. And then the whole thing may be, we may have a final value. That is a different final value, but it will not change in shape. Does that make sense? Yeah? Okay. But that's actually an interesting question, because what happens if, for example, we had a 0 on top of the equation? We didn't deal with that, but let's assume, for example, that on top here, instead of having just a gain, we have a 0. Now we can just add zeros. Let me do it this way: s plus 5 divided by s squared plus 5s plus 5. Now this is a bit different because we have a 0 and minus 5. And how we deal with that? Well, we can split this into 2 functions. We can have s divided by s squared plus 5s plus 5 plus 5 divided by s squared plus 5s plus 5. So you have now 2 functions. And this is a bit different because let's assume that the inverse of this gives you h of t. And the inverse of that gives you h of t. What is the inverse of this? If this gives you h of t, let me put a number 5 here, 1 over 5 and 5. So we have the same. We have basically the same function, but are now multiplied by s. And the same function, but multiplied by s. So what is the time response of that? If this is h of t, what is this one? The derivative of h of t, s h of t. Very good. So this is dh of t dt times 1.5 plus h of t. So what are we doing here? The time response now changed a bit because to the time response, the original function, we are adding its own derivative. So that as 0 is making all the function, we are adding something to the function whenever the derivative is non-zero. So if h of t was like that, we are now adding to it dh of t dt. So all these transients will become sharper because we are adding a component that it depends on the derivative of the function, depends on where the function changes the slope. And notice that it will eventually go to the same value because in steady state, this component here is 0. So that's just to show the difference between the two cases. When it's a constant is fine. It only scales the system up and down. But when you have a 0, the 0 is actually making the transients sharper, right? By adding this component that depends on the derivative of the time response. Okay, but that's not the case. Back to our example here, I kind of went on a tangent line there. Okay, if there are no questions, then let's move on. Let's do exercise 5. Being very productive. So I'm gonna change the screen here. I'm gonna share the screen again. Here it is. So here we have a robotic system that was designed to perform ocular surgery. So it's operating on an eye. The block diagram of such system is shown below, where R of S is the desired position of the tool, that is the surface of the eye. So we want the robot to move to the surface of the eye and stop there. And Y of S is the actual position. So R is where we want it to go. Y is where it is. We take the difference between them, we create an error, multiply the error by K, and that's the command we give to the robot. Any controller overshoot would result in the tool puncturing the eye. That's an interesting example here, because if you want to move the robot to the surface of the eye and stop right there, you can't allow any overshoot to happen. That would mean going into the eye and then coming out and then stopping at the surface. That would create overshoot and it would create damage. So as designers, we now need to tune this controller, this value of K, such that the robot reaches the position without overshooting it. And here is a good example where the time response may not be important. We can afford to let the system be slow, but precise, rather than being fast and oscillate before it settles. So determine the steady state error for a unit step input of R as a function of K. And if K equals to 10, what's the percent overshoot? Determine the maximum value of K that results in no overshoot. And what's the settling time as a function of K? So we have control over K. We don't have control over the plant. So the first question is determine the steady state error for a unit step input of R of S as a function of K. So a steady state error would mean we want the robot to move to the surface of the eye. How close does it get? If it gets to 1 millimeter in front of it, the steady state error is 1 millimeter. Right? But we want that ideally to be 0. It will move to the surface of the eye and it stop right there. Let's do the first example here. They have, oh, okay, I don't have space to solve for this on the slides. So what I'm gonna do, that's my bad here. Find an empty spot somewhere. Okay, let's do it here. Just create a surface here where I can use. Just give me 1 second. It's bad planning from my end here. Just give me 1 second. Okay, let's do it here. So we have a block diagram that looks like this. K, and the transfer function is 1 over S plus 2. Okay, I forgot to add the blank slides for the answer. Sorry about that. The first question is, calculate the steady state error for a step input of R of S. So what is the step input in this case? In this case, we tell the robot to go to, say, 10 millimeters. You see the equation, the desired motion goes from 0 to 10 and it remains at 10. So that's a step input. So this is 1 millimeter. So to find the steady state error, we will need to define the error first, which is right there. That's the error as a function of time. And we are going to define the error then as the desired position R of S minus the actual position Y of S. And what is Y of S? To find Y of S, we need the transfer function Y over R. And I'm going to give you the transfer function value here because I think that's probably clear at this point. Should be that. So Y of S is the transfer function times R. Now we can define the steady state or the error, not the steady state error, as R of S minus Y, and Y is K over S squared plus 2S plus K times R of S. Can factor out R of S. 1 minus K over S squared plus 2S plus K. So that is the error at all times. We want the steady state error instead. So to calculate the steady state error, we can just use the final value and make the limit of when S tends to 0 of S times the error. Where is that S from? That's from the theorem, remember, and R of S is the equation above that we just established. So this is the same as the limit when s tends to 0 of r of s, which is 1 over s times the function 1 minus k s squared plus 2s plus k. What is the result here? What is the result of the operation? So this s cancels that s. And then we have 1 minus k. When all s's are 0, we have k over k. That's k over k is 1. 1 minus 1, 0. So the steady state error is 0 for all values of k. Greater than 0, actually. Otherwise, the system is unstable. Okay, so the steady state error is 0 for all values of k. Positive values of k, because negative values of k would result in unstable poles. So the final value theorem doesn't apply. If the system is unstable, there is no final value. The final value theorem doesn't hold. Yes, so then if you apply a step input, in that case, it would just go to infinity. The robot would go unstable. You can look for videos on YouTube that are unstable robotic arms, and you see what happens. It's a bit chaotic. And that it really happens in practice. It is easy to understand. If you put a negative k here, we are making now the error increase instead of decreasing. We are making the robot go in the wrong direction. So you're always increasing the error instead of decreasing it. And then it just blows. It's a positive feedback loop. Any questions? Any questions from home? Nope. Nope. All right, so let's do the next one then. The next question is, what is it? Calculate the percent overshoot if k equals to 10. Percent overshoot when k equals to 10. So when k equals to 10, we have y of s over r of s equals to 10 over s squared plus 2s plus 10. How do you calculate the percent overshoot? What do we need? What do you need for the percent overshoot? We need the equation of 100e power of na, which is a function of the damping ratio. All right, so yeah. Yes, yeah, that's a different question though, right? Later, here we just want to know what happens if zeta is k is 10. Maybe if it turns out that the damping ratio is smaller than 1, then it would be fine, right? It would be no greater than 1, we have no overshoot. So the first thing is to determine the damping ratio. So s squared plus 2 zeta omega n s plus 10. Oh, sorry, plus omega n squared. So here we have omega n squared equals to 10. Omega n is the square root of 10. Then you have 2 zeta omega n equals to 2, right? From which we can determine zeta as 2 divided by 2 is square root of 10. And this is 0.3162. That's a problem because we don't want any overshoot. So this value of the controller, gain 10, will indeed lead to overshoot, but by a lot of overshoot, because we have here a damping ratio that is smaller than 1. So with that, we can calculate the percent overshoot by just plugging this into the equation for the percent overshoot, which is 100 exponential of negative pi over zeta times zeta divided by 1 minus zeta squared. And this should give 35%. I'm not going to go over that because it's just plugging the number there, right? And calculating it. 35%. So clearly, that's not a good control gain. Any questions? Yep. Yeah, so we got that from here again. We are equating the coefficients of these two functions. And then 2 is 2 zeta omega n here. All right, that's equation 2, equation 1. Okay, so that controller gain is too high, and the system is too aggressive. It results in overshoot. Hence the next question. Well, if this doesn't work, then what is the maximum value of K that results in no overshoot? So in that way, the robot goes just in front of the eye, touches the surface of the eye, but it doesn't puncture the surface of the eye. How do we do that? The maximum value of K that results in no overshoot. Zeta has to be greater than 1, right? Zeta has to be greater than 1. So I'm going to repeat this one more time because I see this is a very common mistake. I'm asking you what is the maximum value of K or the required value of K that results in no overshoot? So what the students do is they take this equation, they equate this to 0 and find the value of zeta. What do you expect to find from this? We know that from a percent overshoot, zeta has to be greater than 1. And this equation is only valid for underdamped systems. Remember that we took the underdamped system equation, we took the derivative of it and solved for it that way. So this is only valid when there are oscillations, when there is damping ratio between 1 and 0. This cannot work then. What is the result here? You probably get don't even know if there is a solution to this equation. It's probably a complex number. This doesn't work. Instead, what you can do is to go back to the original equation and simply find the value of K that it gives a damping ratio of 1 or greater. Okay, so now we want the value of K such that the percent overshoot is 0. This entails zeta greater or equal to 1. And then we can go back to the equation we have here and equate that to the coefficients of the standard form. So we have omega n squared equals to K and 2 zeta omega n equals to 2. From the first here, we get omega n equals to square root of K. And then you have now 2 times zeta omega n square root of K equals to 2. If we want the percent overshoot to be 0, that entails zeta greater or equal to 1. So let's go to the limit here and put a zeta equals to 1. And that tells us that a K must be 1. When K equals to 1, this is a critically damped system. No overshoot. So to ensure that zeta the system has no overshoot, what is the limit of K? This is the upper limit of K. Anything greater than 1 will start to cause overshoot. If you can see that if you calculate the damping ratio decreases with K. All right, so K equals to 1 is the upper bound. Anything between 0 and 1 will make the system overdamped, no overshoot. Anything greater than 1 makes the system underdamped and then overshoot occurs. Why does it start at 0? Because if we put a negative value of K, the system is unstable. So the system is has no overshoot provided that k is between 0 and 1, and then for k greater than 1, we have another damped system. And yeah, so this system is not going to go unstable, but it will get quite underdamped and quite show a lot of oscillations. Yeah. So we have the same numbers again. Omega n equals to square root of k, 2 zeta omega n equals to 2. We can find here zeta as square root 2 divided by 2 square root of k, which is 1 over square root of k. And you can find the settling time as 4 divided by zeta times omega n. This is 4 divided by zeta, which is 1 over square root, this is square root of k. Square root of k times omega n, which is, times omega n is square root of k, 2 zeta omega n equals to 2. Omega n is, okay, yeah, no, that's 4 seconds, and it appears to be constant, in fact. Okay, so if we don't finish today, I'm gonna post the answer here. We have 7 minutes. So the question here is, consider the circuit shown. The input is the current and the output is the voltage VC. Find the state space representation of the circuit. Okay, so where do we start? What is the first step? First step is to define the state variables. And which state variables, how many state variables do we need first of all? How do we start that? What stores energy? Very good. And how many elements are storing energy here? We have 2. We have the voltage across the capacitor VC, and we have the current through the inductor. That's called that IL. There's another element that can potentially store energy. So we'll need 2 state variables. Let's call them X1 and X2. And let's define X1 as IL and X2 as VC. Anything else can be derived as a function of that. Now that we define our state variables, what we are looking for to find the state space equations are equations that will give the derivative of these 2 variables as a function of other state variables and the input. So we need the derivative of IL and the derivative of IC. What equation can we come up with that gives us the derivative of VC? Which equation can we come up with that directly gives the derivative of VC? Any ideas? Well, we can write an equation for VC is either it's the voltage or the current through the capacitor. So if you want the derivative, write the current. So the current through the capacitor depends on the derivative of its current, right? Which is, let's call this IC. Let's call this voltage IR, this current IR. So we could write the sum of all currents, I of t equals to IR. What is IR? Well, let me write this like that first, plus IL plus IC. So the reason for this equation is that we have IC, and that relates to the derivative of the voltage across capacitor. But IR is not a state variable, so we need to get rid of it. How do we get rid of it? Can we write IR as a function of one of the state variables? What is the voltage across R? The voltage across R is VC. And VC is one of our state variables. We could write that I of t is VC over R plus IL, that's a state that can stay, plus C dVC dt. Aha. That's where the derivative of the first state variable shows up. And that's why we went with that equation. So remember, before we start writing any equations, just think about the equations you need and where you're going to find them. Right? Before you just have a collection of equations and then you don't know what to do with them, think about what variables we are actually looking for. So from this, we have dvc dt times c equals to I of t, which is the input, so it can be there, minus vc over r, that's a state variable, and the minus il. So if vc is x2, then vc dt is x2 dot equals to I of t over c, minus vc is a state variable, that's x2 times rc, minus il, which is another state variable, x1 over c. Okay, so this is x2 dot. And then I divided everything by c. Make sense? Okay. So now we did half of the problem here. We have the derivative of one of our states. Now we need the derivative of the other state that is only a function of the states themselves. And that is the derivative of IL. So before you write any equation, let's think about it. Which equation will give us the derivative of IL? How can you get in an equation the derivative of IL? The voltage across the inductor is proportional to the derivative of IL. So let's look at that. Let's now look for an equation where the voltage across that inductor appears. And which equation can we use? Well, we can use pretty much any loop. We could use this loop or that loop. Doesn't matter. Let's use this loop here and do Kirchhoff's law around this loop. Now notice that when we go on VC, like that, when we do that loop, we have positive, negative, positive, negative, positive, negative. So when we go through the capacitor, we have a positive voltage. When you go to the inductor and the resistor, we have a negative voltage. So what does that give? That gives VC, voltage across the capacitor, minus R times IL, that's the voltage across the resistor, minus the voltage across the inductor, L DIL dt, and this is equal to 0. See, state number 1, the derivative of state number 1 is showing there, and everything else in that equation is a state. Everything else in that equation is a state. So you now can solve for L di dt, that's VC minus R times IL, and then you can write this in the state space format. So DIL dt, IL is x1, so DIL dt is x1 dot. VC is x2, and IL is x1. And that's the equation for x1 dot. Okay, so with these two equations, we can now put this in the standard, in the matrix form. From now on, that's easy. We don't have time to do that, so we're going to stop here.